All right, gee, it's all yours. Please go ahead.
Thanks, Daniel, for the introduction. Can people hear me well and see my screen?
Yes, we can hear you and see.
Good. Let me just bring up my laser pointer. Oops, sorry. Right. Hi, everyone. Thanks for tuning in. So today I'll be presenting about our work on experimental results on dissipative Landau Zener transition performed on a superconducting flux qubit, where we found evidence of a crossover from the weak to the strong coupling limit. So this work was mainly done by me and my colleague Robin from University of Waterloo, and with help from our colleagues in the device design and Lincoln Lab on providing the experimental infrastructure and fabricating the device, and also USC for providing the theory support. And this work is based on our recent archive preprint here. Okay, so for today's talk, I'll start by introducing the dissipative Landau Zener tunneling problem, and I'll first talk about the previous results in the weak and strong coupling limit, which will provide a lot of the intuitions in order to interpret our experimental data. And I also discuss briefly the relation between Landau Zener tunneling and quantum annealing. Then I'll talk about the experiment setup, our device, and how we characterize our device to perform in order to perform the Landau Zener measurement. Then I'll discuss the measurement results and simulations to compare with the experiment data. And finally, I'll touch on the implications and the future steps. Okay. So the Landau Zener problem is a well-known problem where two states are brought together linearly, forming an anti-crossing in the middle of the sweep, and then going away again. So the question is, if you start in the infinite past in the ground state, that is this blue state here, what is the probability to find the system in the blue state at the end of the sweep, given some tunneling amplitude delta and the sweep velocity v? So in the coherent limit, this problem is solved, and given the transition probability is given by this expression here, which depends on the tunneling probability and the sweep velocity exponentially. So following the adiabatic evolution. Right, and this problem is relevant for a wide range of physical phenomena, including atomic collisions, chemical reactions, molecular magnets, and of course, quantum annealing. And physical realizations of the Landau Zener problem is always going to be affected by coupling to the environment and dissipation. And there has been a lot of interest on theoretical modeling of the dissipative Landau Zener problem, which I have given a few references here. So when we consider the effect of the environment and on the Landau Zener transition, so we usually consider the system path has a coupling that is proportional to the sigma z operator of the system. coupled to some environment operator Q here. And in the weak coupling limit, that's the limit where the environment causes thermal transitions between system energy eigenstates, and that can usually be captured by the Fermi golden rule, which says that the ground and excited state transition probability is given by this system operator sigma z, its matrix element squared multiplied by the noise spectral density of the environment operator. And this is a kind of rates that you would expect in typical gate-based model computations. But the Fermi golden rule only applies for time-independent Hamiltonian. For time-dependent Hamiltonians, work has been done to extend this to describe this kind of transition, which is formalized as this adiabatic master equation approach. When applying this adiabatic master equation to the Landau Zener problem, it has been predicted that in general, coupling to the environment will produce a non-monotonic dependence of the transition probability on the sweep velocity. And that's given by this graph here. We can start to look at this graph from the right-hand side, corresponding to very fast sweeps. So, or short sweep times. You can see that the transition probability is always close to the coherent transition, Landau Zener transition probability, corresponding to the system behaving almost coherently. And in the intermediate sweep time regime, we see that the transition probability tends to go to 0.5, which corresponds to the system thermalizing across the minimum gap, and the thermal state near the minimum gap is close to 0.5. And as you extend sweep time longer, you see that the transition probability start to increase again, and that corresponds to the system thermalized into a state that is close to the thermal state near the end of the sweep. And these two thermalization occurs at different time scales because we are considering sigma z coupling, and sigma z coupling couples the two states more strongly near the gap. Hence, thermalization near the gap is faster than at the end of the sweep. So if the environment is instead has a strong noise power spectral density, and in particular, if it's also low frequency dominated, we'll see that the transition between the left and right state is instead described by this macroscopic resonant tunneling process, where the transition rate in general follows a Gaussian dependence on the external bias, and the width is and the environment will first broaden the transition rate by width W, and the transition, we also see that the transition has a particular bias, epsilon p, and epsilon p and w are given by the integrals of the noise power spectral density. So the way I like to think of this is that in the strong coupling limit, the system has no coherence, so that it can so that means there's no off-diagonal element in the system density matrix, so it is always in the left or right state. And we would see that so the environment low frequency noise would first broaden the transition rate between the left and right, and then we'll also see that the maximum rate doesn't occur when the two wells are equal in energy, but it occurs with some bias epsilon p. And people have been using this measurement to determine the low frequency noise in quantum annealing systems, flux qubits in particular. And this is a measurement that was performed by the Google team, where we see the transition rate being broadened, and there's a bias between the left and right and right-left transitions. And we also have the measurement done on a D-Wave device, where we can see that there's a much larger width, and the separation between the two transitions are also larger, meaning the low frequency noise in these D-Wave devices are much larger. So if we apply the microscopic resonant tunneling MRT theory to the Landau Zener process, what we get is that the dynamics is completely described by a rate equation. And that was, again, because there's no off-diagonal element in the system density matrix. And the transition rate is simply given by this MRT left and right transition rates. And if we take some typical noise parameters that would correspond well to the D-Wave qubits, we have the left and right transition rate, these two transition curves are pretty well separated. So when they are well separated, what we will find is that we can pretty much neglect the second term in this rate equation. That is because when we start on the left, the system, so the left to right transition is only peaked on the right, and the right to left transition, when this term is large, this second term is always small, and when this term is large, this gamma right to left is always small. So and to find the final transition probability, you'd only need to integrate the left to right transition rates. And that will give you, quite surprisingly, the transition rate would be pretty close to the coherent transition rate when you plot this residual left state probability as a function of the reduced sweep time here. And if we instead have the two left and right transition curves overlap, that is when the epsilon p is 0, you'd see that the curve would start in the short time limit. It still follows the coherent limit, but then it would peak at 0.5, which makes sense because if the left and right transitions have equal rates, and you let the system having enough time to for this transition to occur, the final system state would just be at have equal probability of being found in the left and right. And so generalizing this MRT theory leads to the Polaron transformed master equation, and this incorporates the multi-qubit case and also the effect of high frequency noise, which was used to describe a lot of the data measured on D-wave. So how is Landau Zener related to quantum annealing? So quantum annealing is mainly about solving optimization problems based on finding low energy states of an Ising Hamiltonian. And often dissipation is an important factor when considering the success probability of an annealer. And there have been many previous literatures discussing what would happen when the system bath coupling is in the weak coupling limit, and what would happen in the strong coupling limit. So in the weak coupling limit, you can imagine that there's a trade-off between adiabaticity and thermal excitation. Sorry. If you evolve too fast, you get the evolution becomes diabatic, which brings you out of the ground state. If you evolve too slow, then there will be thermal excitations near the minimum gap, which would bring you also out of the ground state. And in the strong coupling limit, tunneling occurs between entangled system bath states, and the system tend to be localized in some local minima and not being able to find the tunnel to the global minima. And also there's in general limited exploration in both theory and experiments in the intermediate regime. And therefore, we believe during the dissipative Landau Zener transition measurements could provide some insights to the evolution of the annealer through a small gap. So, has there been any questions so far?
So far, so good.
Okay, great, thanks. Okay, I'll next talk about the experiments, but I also realized that we are already 20 minutes in, so I'll try to speed up this part and try to get to the measurement results and the simulations. So the device we use to perform this experiment is a capacitively-shunted flux qubit. It can often be described by this two-level qubit Hamiltonian, where we have the longitudinal term with magnitude epsilon, and transverse term magnitude delta, and the longitudinal term epsilon is controlled by the Z-loop flux bias, and the transverse term is controlled by the X-loop flux bias. And here I'm showing the chip on which we perform the device. So this is actually a chip that was designed to test a couple of the design primitives that were going into the larger quantum annealer, and the qubit we are performing the experiments on is actually just this part here. So besides the qubit circuit itself, we also have the control elements, including bias lines for each of the loops, and also a microwave drive that's capacitively coupled to the flux qubit, which allows us to do standard characterizations like spectroscopy and T1, T2 measurements. So for readout, we inductively couple the qubit to RF squeeze terminated resonator, and by reading out the transmission through the resonator, we can read out the persistent current state of the qubit because the resonator frequency is flux sensitive. And the Landau Zener protocol is basically you will start by preparing the qubit in the left blue state, and by sweeping the external bias of the Z flux within some time TLZ, and finally measuring the transmission of the resonator, we can back out the Landau Zener transition probability. So but this is operation is an ideal case, and one of the main problems we had to deal with on this device is crosstalk calibration, and we found that there is significant crosstalk between the flux bias lines and target loops, and this becomes particularly challenging to calibrate because our flux qubits in general have a pretty strong flux coupling between the elements, like the qubit and the couplers or the resonators. And this is generally true for this flux qubit based annealers, where we also want independent control. And during the program, we developed two different methods to calibrate these flux crosstalks. And the first one is this iterative calibration, where the idea is that when we do calibration in the first round and try to sweep the control voltages, we found that the system does not respond in a periodic pattern. But nevertheless, we can assume it is nearly periodic and extract the corresponding crosstalk matrices. And in the next iteration, we can make use of the previously obtained crosstalk and sweep in a compensated coordinates and gradually restore the periodicity in each round. So, and eventually you just need to multiply the crosstalk obtained in each iteration together to get the final estimated crosstalk. So this was a work that has already been published. And later on, we've also developed another methods, which is based on optimizing for the periodicity of the superconducting flux loops, where the idea is that we can define an control coordinate that is in this form, where we have a identity matrix and the compensation matrix multiplied by the control voltages, and by optimizing the elements of this compensation matrix until we observe periodicity in each flux control coordinates, we can directly obtain the compensation required to compensate for the crosstalks. So the result is that by applying this two different crosstalk calibration methods, we found that both can allow us to achieve an control accuracy of about 2 to 3 millifinode, which is comparable to the crosstalk calibration results in tunable transmit devices. And we think that optimization for periodicity in particular has future potentials as the cost landscape is well behaved, and it reduces the number of data required for the calibration. So that is something that we think has potential to be used in larger scale devices, and that's something we would like to explore in the future. So after calibrating the crosstalk, we performed spectroscopy measurements on the qubits, and by fitting the spectroscopy data, we can obtain a full circuit model. And we also performed T1 and T2 measurements. In the graph here, we're showing the Ramsey measurement as a function of Z flux bias for different X flux bias points. And fitting to this data allows us to determine the low frequency flux noise amplitudes listed here. And it also allows us to confirm that our device's coherence is limited by intrinsic flux noise. And later on, we can use these numbers that go into our open system and simulations. So after finishing the characterization, we start the Landau Zener problem by just looking at the results for the short times. So as I mentioned earlier, no matter whether you are in the weak or strong coupling limits, we'd always expect that at short times, the evolution will follow the coherent limit. Sorry. So we measured the final excited state probabilities for different TLZ and phi x. We call phi x controls the minimum gap delta. And we fit the initial decays to the coherent limit result and extract a effective gap delta LZ. And when we compare the effective gap extracted with the circuit model, we see that they agree very well. And And this is based on a circuit model fitted to just the spectroscopy data, which is at high frequency. And we use the circuit model to predict the low frequency gap, which agrees very well with the effective gap of the Landau Zener transition. So this confirms that our, in general, our measurement setup is working good, and our readout is working good. Then we look at the full range of Landau Zener data. So we can start by looking at the large delta case. For example, this orange line here, we see that at short times, it follows a coherent limit. And at intermediate times, it starts to go to 0.5. And then at long times, it starts to, the final ground state probability starts to increase again. So this general trend agrees pretty well with the weight coupling limit result. And as we look at the smaller delta case, again, the short time result follows closely the coherent limit result. But at long times, it no longer has this non-monotonic dependence, but instead it just goes, the ground state probability just increases monotonically with increasing sweep time. And in particular, at long times, the final ground state probability for the smaller gap data is higher than the final ground state probability for a larger gap. And to simulate the results, we only considered sigma z phi z flux noise, and this is because based on our estimates, we found that the X flux noise is not going to have any significant impact. Sorry. And we consider a combination of 1/f and ohmic noise spectrum for the flux noise, which is common in flux qubits. And as I mentioned previously, the T1 and T2 measurements allow us to determine the noise amplitude, the symmetrized noise and amplitude. But because the anti-symmetrized noise power spectral density will also be important, we assume the bath is in thermal equilibrium at our fridge operating temperature, which is 20 millikelvin. So we use this phenomenological thermodynamic model to account for a difference in the positive and negative frequency part of the power spectral density. So in the weight coupling limit, we use a adiabatic master equation, which is suited for weight coupling Markovian bath. And again, it confirms the non-monotonic dependence, which has been found previously, and which is due to competition in adiabaticity and thermal transitions near the minimum gap and towards the end of the minimum gap. And it agrees with our data in the large gap limit. And in the strong coupling limit, we use the Polaron transformed master equation suited for strong coupling to the environment. The Polaron, the PTRE uses directly the MRT width and epsilon p, which we deduce from the 1/f noise. And again, because our T1, T2 measurements is only sensitive to the symmetrized noise PSD, the anti-symmetrized part, which gives epsilon p, is determined based on this thermodynamic relation here. And running the simulation gives that the final ground state probability just increases monotonically with increasing sweep time. And here I also have to use a 4 times larger MRT width than was predicted using our 1/f noise amplitude. And this is quite common in other flux noise, flux qubit devices, in that typically when you measure the MRT width, it comes out to be a bit larger than the integrated 1/f noise. So we can also compare our measurement with our simulation by plotting the final ground state probability versus the dimensionless sweep time. So this definition allows us to isolate the effect of the environment and the effect of the adiabaticity. So you can see that in either the AME corresponding to the weak coupling or the PTRE, corresponding to the strong coupling, the ground state probabilities for different phi x almost collapse onto a single curve. Whereas in the experimental data, we clearly see a shift of the final ground state probability towards the coherent limit as we decrease the minimum gap. So this also signifies that indeed we are seeing a transition from the weak to the strong coupling limit. So just to summarize, in the short evolution time, the experimental data shows that it is always close to a coherent evolution, no matter whether there is a gap is large or small. And then when the gap is large, there's a non-monotonic dependence of PG on the sweep time TLZ, which agrees with the weak coupling limit predictions. And as the gap becomes smaller, the final ground state probability becomes monotonic in TLZ, which agrees with the strong coupling limit predictions. And finally, in this, we mentioned that in our experimental data, we have a crossing of the final ground state probabilities for different gap sizes. In particular, at long evolution times, the final ground state probability is higher when the gap is smaller. So this is my final slides. So in relation to quantum annealing, just want to highlight that I think our work is another example of where we can use to improve our understanding of open quantum system effects for quantum annealing. And in particular, we have seen more results recently that having larger bandwidth and custom control schemes will open up different perspectives compared to many previous investigations done on the D-Wave device. And having this more flexible controls will always give us more information about the open quantum system. And in particular, we think that understanding the environment reorganization energy, which gives the MRT energy bias epsilon p, could be crucial for the new control schemes, such as the diabatic quantum annealing, which was proposed by Elizabeth Grosson and Daniel Leader. For the next steps, we are pursuing better models, whether it's numerical or just analytical, to better understand the intermediate coupling region results. And we also have DQA experiments planned to better probe the environment reorganization. Yeah, so I have final acknowledgement slides to acknowledge our sponsors. DARPA and IARPA supported this project. That's the end of my talk. I really apologize for the slides presentation going back and forth. I really don't know why it's on my computer.
Oh, well, thank you very much, Xi. And you have nothing to apologize for. It was a very well presented talk, very clear. Thank you. So we have some good amount of time for questions. Does anybody have any questions or comments?
Okay, may I ask a question? This is Hideyoshi Nishimori.
Please.
Oh, hi.
Yeah. Okay. Hi. Can you show me the previous slide, number 18?
Yeah.
Yeah. So you said that data doesn't match either the strong or weak coupling master equations. So is that what you said? Oh.
Yeah.
So you said you need some better formulation of the theory, including intermediate regime. Is that your conclusion?
Yeah.
I see.
We don't have. Yeah, so we have these two different models that corresponds to the weak and sort of strong coupling limits, and we can kind of see that the experimental data, when the gap is large, the weak coupling limit results agrees pretty well with the experiment, and when the gap is small, the strong coupling limit result kind of agrees with the strong coupling limits. And so our experimental data kind of interpolates between this weak coupling behavior to the strong coupling behavior as we reduce the gap, but we don't have a single model that describes the transition from the weak coupling to the strong coupling.
Okay, I understand it. So you say that this does not necessarily apply only to the single qubit case, but it may apply to a larger system. Is that what you suggested in the next conclusion slide?
Yeah. So so the experiments is only for single qubit, and it's only for the Landau Zener transition. When considering a larger qubit, if it's a similar process where if it's a problem which is similar to the Landau Zener transition, where you are going from one well to another well, I think this result can still apply. But for larger number of qubits, larger systems, this might not always be the kind of minimum gap or situation you'd have. Like, for example, if we are annealing or forward annealing a ferromagnetic chain, you just go from a paramagnetic state to and you do not have this kind of situation like a Landau Zener where you're going from one well to the other well. It could be different.
Okay, thank you.
Yeah.
So just to follow up on this, if you stay on the slide, so the only model that exhibits the clear non-monotonic behavior for a fixed gap size is the AME.
Yeah.
Right. Yeah. So at least in that sense, qualitatively, it seems like the AME is in pretty good agreement with all the data, unlike any of the other models. Would you agree with that?
It agrees more, but yeah, as we have discussed earlier, that the AME also doesn't produce this crossing of the ground state probabilities for different phi x.
Right. Yes. And do you have any ideas at this point why this crossing happens? And just to be clear for the audience, so maybe you can point out again exactly what we mean by this crossing. It's a crossing of curves.
So either in the AME or the PTRE, so if we just look at the AME specifically, you will see that the larger gap, when the delta is the larger delta curves, that's like this orange curve here, is always higher than the smaller gap delta data. So the ordering is always the same, no matter what's the evolution time. So the orange curve is always on top of the blue curve. And when we look at the PTRE, it's also the same. The orange curve is always on top of the blue curve. The larger gap data always gives higher ground state probability. But in the experiment, that's not the case. For short evolution times, the orange curve is higher than the blue curve. But as you go to long evolution times, the blue curves becomes higher. So there's a crossing of all these different curves that happens around here.
Yeah. So just to summarize, it's not so much that we don't have a model that works well in the intermediate coupling regime. It's more that the AME does a good job for relatively short anneal times or Landau Zener times. But then it misses this feature of the inversion of the order of the curves at long Landau Zener times. Whereas the PTRE seems to not do a very good job overall, because it misses both the short and the long Landau Zener times. So it seems like what is missing here is a model that can capture this inversion of the order of the curves at long Landau Zener times. Is that fair?
Yeah. So I still not sure that the AME describes all the short evolution time, and I think the short evolution time data is just not distinguishing enough. We've seen the Landau Zener based on MRT theory, which predicts that the short evolution time it still agrees with even if you're in the strong coupling limit, it's still close to the coherent limit, so which you can't tell apart with the weak coupling limit result in the short evolution time. So yeah, I think it's not necessarily that the AME only fails in the long evolution time limit. I think there's still environment reorganization that becomes significant as the minimum gap is reduced. And yeah, so when the gap is large, the system can preserve, or larger, when the system minimum gap is larger than the some parameter of the environment, the system can preserve its energy eigenstate. And as the gap becomes smaller, the noise becomes more dominant, and you're transitioning into this incoherent tunneling regime, like the MRT.
Mm-hmm.
But yeah, I guess we're still doing some numerical explorations, like trying to find out what kind of what parameter of the environment is really determining whether we are in this weak or strong coupling limit, I guess.
So we have time for one more question.
Can I ask a question?
Please.
This is Sei Suzuki. Hi.
Oh, hi.
In your two simulations for weak coupling and strong coupling, is the model parameter common in both simulations?
It's not quite common because these two models they take slightly different parameters. So in the AME, it is just the noise PSD we're giving in, which has 1/f plus an ohmic component.
Mm-hmm.
In the PTRE, the strong coupling model, the low frequency part, which is a 1/f part, that PSD gets integrated into two parameters, which are this W and epsilon P.
Mm-hmm.
This MRT width and the reorganization energy. So the PTRE has the ohmic high frequency noise part, but the low frequency part is just described by these two parameters.
Okay, so in the weak coupling simulation, there is a low frequency 1/f noise, right?
Yeah, and I should also say that the low frequency part, so we impose a cutoff on that noise PSD.
Okay.
Because it would be divergent otherwise. So the low frequency cutoff we impose is 10 megahertz, which corresponds to the minimum gap, the smallest minimum gap we have in the measurement.
I see. And is the you chose the power of spectral density, which was 0.9 or something?
Yes.
0.91.
Sorry. Yeah. So this is based on. So this is the 1/f like noise. 0.91. We didn't use 1 exactly, but 0.91 because we have some other data points in previous literatures where the same fabrication process was used and was found that 0.91 agrees better than just exactly 1. But I think I also have simulation where I used 1 instead, and the results is similar.
Oh, I see.
Yeah.
So your result doesn't depend on the detail of this power.
Right, it doesn't.
Okay, I see. Thank you.
Yeah, no problem.
Sorry, can I ask one more quick question as well?
Yes, please.
Yeah, right.
Go ahead.
So in the very last slide, in the PTRE, in the strong coupling regime, there are 2 curves, right? So I'm just wondering, why do we choose 4W rather than any other power factor of W? Was there like any fitting involved in choosing this particular factor? Or?
Right, that's a good question. So they have the 2 curves here labeled as PTRE and PTRE4W. So PTRE uses noise parameters as estimated by our T1, T2 measurements, and you see that it the ground state probabilities like flattens out towards 0.5, and that's by just numerical exploration we found is because there's the environment reorganization energy is too small, and the left and right transitions are not well separated enough to match the data. So choosing 4W as just a number we used to have the results look similar to our data. And we have also compared previous MRT measurements where this W is explicitly measured in both D-Wave devices and the Google devices, and we found that the W is, when you directly measure it, it's always about 2 to 10 times larger than what you'd get by integrating the 1/f noise.
And that's because there are other sources of noise that you're not considering the model, or?
Yeah, so it's I guess it's because our T1, T2 measurement, which we use to deduce our 1/f noise amplitude, is not sensitive enough at all the frequency ranges. And when you assume a simple 1/f noise, you are probably missing. There are small deviations from the 1/f power spectral density, and that could lead to slightly larger noise.
Okay, and this wouldn't affect the validity of the result for the recoupling regime, or?
Yeah, the wake coupling. So what we are comparing here is more of a the qualitative feature. We are not claiming that we can get quantitative agreement between the simulation and the data.
Okay.
Yeah.
All right. Thank you.
Yeah.
Is there another last question? Okay, if not, then thank you again very much for a great talk. And thanks everyone for attending. And see everyone hopefully at the next seminar next week. Here, bye-bye.
Thanks, Daniel, for hosting it. Thanks.